Hi, I'm Kirsty Duffy, and welcome to Fermilab's new video series about the tiniest, most fundamental particles that make up our universe. This is Even Bananas. Today, we are starting with a mystery. In the early 1900s, physicists were beginning to understand the building blocks of nature. They knew that matter was made out of atoms containing a positively charged nucleus surrounded by negatively charged electrons. But there was a mystery at the heart of the atom. Scientists discovered that one atom could turn into another by a type of radioactive decay called beta decay. And they'd seen it with an element called bismuth decaying into a different element called polonium. But nowadays we're more familiar with carbon-14 decaying into nitrogen. That's the process that allows carbon dating, which is how archaeologists determine the age of ancient human bones. So in beta decay, an unstable nucleus transforms into a different nucleus with the same mass, but with one extra positive charge, emitting an electron in the process. And this kind of makes sense. Physics is all about things being conserved, and here we see the electric charge is conserved before and after the decay. Because after the decay, you have one extra positive charge in the nucleus, but also one extra negative electron being produced as well. So, we're good so far. But another quantity should be conserved in these decays as well, which is energy. The beta decay process that they discovered at the time was what scientists called a two-body interaction. Because after the decay, you have two things, or bodies in science speak, the new nucleus and your electron that you've made. And if our new nucleus isn't moving, then all of the energy from that radioactive decay should be carried off by the electron. So when scientists looked at the electrons produced by beta decay, they expected them all to have exactly the same energy every time, like baseballs being fired at you by a pitching machine set to one single speed. But that's not what they saw. Instead, the electrons had a whole range of energies, kind of like popcorn coming out of one of those old-fashioned poppers. And that was a major problem in physics. It was actually a problem for more than 15 years. And it's really weird to think about now, but at the time, some people even suggested that the law of conservation of energy might be wrong, and that's why energy wasn't being conserved in this decay. Luckily for us, in 1930, Wolfgang Pauli came along with a surprising solution. He suggested that beta decay actually produced an unknown third particle. And that would resolve the conservation of energy issue because a three-body interaction would allow some of the energy to go into that third unseen particle, and then our electron could take on any of the range of energies that the scientists had seen. This new unknown particle would have to be electrically neutral, very lightweight, maybe even massless, and of course it had to be very difficult to spot, to explain why the scientists had never seen it before. Soon, this hypothetical particle was dubbed the neutrino, Italian for little neutral thing. But Pauli was actually really upset about that last point on the list, about it being very difficult to spot. In fact, when Pauli proposed the neutrino for the first time, he said, "I have done a terrible thing. I have postulated a particle that cannot be detected." Luckily for us though, Pauli was 1 for 2 with his predictions. Neutrinos do exist and they are the solution to our mystery. And we can detect them, although it took another 25 years for that to actually happen. The discovery of neutrinos was actually a really important milestone in the history of physics, and it's raised even more questions that scientists are still trying to answer today. And that's where I come in. I'm Kirsty Duffy, I'm a physicist at Fermilab, and I'm working to understand the weird and exciting world of neutrinos. I'm part of the microgrid experiment, and I'm also working on the NEAR detector for the Deep Underground Neutrino Experiment, or DUNE for short. We'll get into both of those experiments and others in future episodes. I am so excited to share with you what makes neutrinos my favourite fundamental particles, because we've all got one, right? And to tell you about some of the incredible experiments we build to study them on our new series, Even Bananas. And I'll leave you with one fun fact. We talked about neutrinos being hard to spot. The neutrinos from the sun are so antisocial that they could pass through several light years of solid lead without being absorbed. So the Earth and all of us on it are absolutely nothing to them.